Alright, let's get started with the foundation of sequential decision analytics. Every sequential decision problem, no matter how complex it looks, can actually be described using 5 simple elements. What are they? Here, these 5 elements form what we call the universal framework for sequential decisions. So the first one is the state, and we usually write it as T or S sub T. The state represents everything we need to know at time t to make a decision and to model what happens next. In practice, this might include inventory levels, customer demand, or even the position of a vehicle, whatever defines the current situation of the system. Next, we have the decision written as like that, x sub t. This is the action or control we choose at that time. It could be how many units to produce, how much to order, or which route to take. Is always chosen from a feasible set, which we usually call capital X sub T. Okay, then comes information here. And what is that here? Let's look at this. This one represents the new information that arrives after they make our decision, like random demand, a price change, or a machine failure. It's the uncertain part of the system, the thing we can't control but must react to. And here, fourth piece is the transition function. It is what moves the system forward. In notation, we write it as like that, you can see. And it tells us how today's state combined with our decision and the new information creates tomorrow's state. And finally, we have the contribution function C. This measures what we gain or lose from taking a decision in a given state, for example, profit, cost, or reward. And sometimes it's written as like C, I mean here C, ST, XT, and other times C, ST, XT, W sub T plus 1, if it depends on the random outcome too. So look at this. There is a golden rule here. Model first, then solve. Before jumping into algorithms or methods, the idea is to clearly describe your problem using these 5 elements. Once that model is solid, then you can explore which policy class works best for your structure. So, here, what's a policy class? General goal here. What is that? The objective function we try to maximize is written like this. Okay, maximize our policy pi in a capital pi of capital F superscript pi equals the expected value of the sum over t of gamma to the power t times c of s sub t and x superscript pi of s sub t given s sub 0. What this means is simple. We are looking for the policy that gives us the highest expected total reward or the lowest expected total cost over time. Now, these 4 policy classes are divided into 2 groups. The first group is called policy search, and the second is here, look ahead. In the policy search group, we have 2 types. The first is PFA, which stands for Policy Function Approximation. This is when the decision rule is a direct function of the state and some parameters, and mathematically we write it as like that, equals a direct parameterized function. The second is CFA, which stands for Cost Function Approximation. This one chooses the action that minimizes an approximate cost function, written as like that, you can see. Then we move to the look ahead group. The first class is VFA, I mean value function approximation. This one chooses the decision that maximizes immediate contribution plus an estimated value of the next state. And it is written like that here. And the last one is DLA, I mean direct look-ahead approximation. And here, instead of looking one step ahead, we optimize our several future decisions directly, like that. And here we will look at key concepts. Okay, each of these four classes covers a wide range of methods. For example, simple heuristics and neural networks both fit under PFA, while stochastic programming and model predictive control fall under DLA. And there are a few key ideas to remember here. And what are they? First, the coverage is universal. I mean, every method in the literature fits into one of these four classes. And second, the right choice depends on the problem. No single class is best for everything. And finally, these can be combined. Hybrid approaches like actor critic or Monte Carlo tree search use more than one class together. And when you look at the research landscape, you will find that over 15 different fields like dynamic programming, stochastic programming, reinforcement learning, and optimal control are all just studying these same sequential decision problems through different lenses. Okay, now we will look at PFA. Let's continue. Policy function approximation. Okay, here a PFA is the most straightforward kind of decision rule, and it is any parameterized function that takes the current state of the system and directly maps it to a decision. We usually write that as like that. You can see x superscript PFA of capital S sub t given theta equals f of capital S sub t semicolon theta. In plain words, that means we use a function f defined by some parameters theta to decide what action to take at time t. Now, what can this function f actually be? Look at this. Well, it can take many forms depending on how simple or complex your problem is. For example, it could be a lookup table like a tabular policy that says if you are in this state, do that. It could also be linear like that. What is that? Theta transpose pi of capital S, where pi s represents features of the state. Or it could be something more flexible like a neural networks or a decision tree. And essentially, f can be any function, parametric or non-parametric, as long as it maps states to actions. So in this approach, we don't explicitly simulate future steps or compute value functions. Instead, we directly learn or tune the parameters theta so that this mapping performs well over time. And let's make it concrete with a simple example. And look at this here, the classic capital S inventory policy. Here our parameters theta are made up of two numbers S and capital S. The parameter S is the reorder point and capital S is the order up to level. And here the logic works like this. If your current inventory, let's call it R sub t, drops below the reorder point S, you place an order that brings the inventory back up to S, I mean capital S. So mathematically, we can say that here if R sub t is less than S, then Q sub t equals capital S minus R sub t. Otherwise, here Q sub t equals 0. And that's it. Okay, simple, interpretable, and it captures a practical rule many companies already use. Now, depending on your data and application, PFAs can take on very different forms. So what are they? For instance, a buy low, sell high strategy in finance can be expressed as like that. What is that? buy if the price is below a certain threshold theta buy, and sell if it's above theta sell. Another one is the affine policy here, and what's happening here, written as like that: x equals theta 0 plus theta times capital S, which is commonly used in robust optimization. And in reinforcement learning, actor networks like pi theta of a given S in PPO or SAC algorithms are also PFAs, and they directly output actions from states using neural networks. And look at this. When we simulate this kind of inventory policy, you can see how the inventory level behaves over time. And here, the green line represents inventory, the dashed blue line shows demand, and that orange dot line here is our reorder point. Okay, let me show you. Every time the inventory dips below that orange line, a replenishment happens, pushing it back up to the order, up to level capital S. And this pattern repeats itself. Stock drops as demand consumes it, then jumps up again when we reorder. That sawtooth shape, you see exactly what a well-behaved inventory system looks like under capital S rule. Remember, like that. Okay, and let's look at this part. Okay, so what is good about PFAs? Well, they are easy to implement, they run fast, and they are interpretable. You can look at the parameters and immediately understand what the policy does. Plus, scaling parameters like S and capital S to match different system sizes is pretty natural. But there are challenges too, of course, and tuning the parameters data can be tricky. You might have to search over a large space or use optimization methods to find the best ones. And also, PFA's flexibility is limited by the form of the function you choose. A simple linear model might miss complex nonlinear relationships, and finally, you usually need to run simulations or apply optimization techniques to discover the best performing parameters. And that brings us to parameter tuning problem. Finding the optimal theta star here, look at this, means solving a stochastic optimization problem. And the goal is to maximize expected performance, which we write like this. Okay, you can see here. And to find that optimal theta, we can use several approaches. What are they? Stochastic gradient descent, finite differences, evolutionary algorithms, Bayesian optimization, or policy gradient methods. Each of these tries to tweak the parameters to make the policy perform better based on the simulated or observed outcomes. And that part is done. Let's look at class 2. Okay, CFA, cost function approximation. So, what exactly is a CFA? Let's talk about this. Well, instead of mapping states directly to actions like we did with PFAs, here we actually solve an optimization problem at every step, but that problem itself depends on some parameters which we will call theta. And you can see the mathematical form right here, like that. And basically that means we are choosing the best decision X by minimizing a cost function that can change depending on theta. And theta here is what lets us handle uncertainty. It modifies either the cost coefficients or the constraints. And now look at the base deterministic model at the top. That's just a standard optimization. Here you can see. And when we introduce theta, we make that model flexible. Theta could represent how aggressive or conservative we want the solution to be. For example, in stochastic systems like energy storage, logistics, or forecasting, that small tweak gives us a way to adapt to randomness without completely rebuilding the model. And if you look at the yellow box, it says CFAs bridge deterministic optimization and stochastic problems. That's the key idea here. We take something we already know how to solve, like a deterministic linear program, and then we wrap it with parameters we can tune later using data or simulations. And okay, let's continue. So the objective function for a CFA looks like this, and maximize here our theta of capital F pi CFA. Here theta equals expected value of the sum over T of C, and SD x pi CFA SD theta. That's so the important part here is where we evaluate it, not in the simplified look-ahead model, but in the base stochastic model. That's where reality comes in, your simulator, your production system, or the real world. And example time, here you see energy storage with forecast. So here theta is a forecast multiplier. If theta is less than 1, you are being conservative, maybe underestimating demand. If theta equals 1, you are trusting the forecast exactly, and if theta is greater than 1, you are being aggressive, maybe assuming higher demand than predicted. Okay, and when you select that theta value in the demo, you can see how it changes the cost outcome, okay, like that. The optimization problem becomes, what is that? Let's look at this. Minimizes the sum from t to t plus h of c times xt subject to storage dynamics and modified demand equals theta times forecast. Okay. Now, the comparison between CFA and industry heuristics is actually really interesting. In practice, people often use simple tricks like add safety stock, use buffer time, or inflate forecasts. And these are heuristics, right? But when we write them in CFA form, they are no longer arbitrary, they are parameterized. Okay, and that means we can tune theta systematically to find the best result instead of relying on experience or guesswork. And CFAs basically turn those intuitive rule of thumb adjustments into something you can mathematically optimize. And if you look at the chart, it shows a performance comparison. Let me show you here. The x-axis is a forecast error. If you cannot read, sorry for this. And y-axis is the total cost. And here the gray gray line represents the deterministic model where theta equals 1, and here the blue line is here. The tuned CFA shows that it consistently achieves lower total costs across a wide range of forecast errors. So by tuning theta, you can make the model much more robust. So let's look at this. Yes. Why do CFAs work so well? There are four main reasons, and you can see them listed here. First, inherent scaling. Theta often hovers around 1, so the tuning process is stable and efficient. Second, domain intuition. People already understand what buffer or safety factors mean, so it's easy to interpret. Third, simulation versus model. And you can simulate complex systems but keep the optimization simple. And fourth, computation efficiency. Because the core solve is deterministic, you can afford to run many stochastic simulations to fine-tune data. So in short, CFAs give you a middle ground. You get the power of stochastic optimization, but with the simplicity and speed of deterministic models. And here, finally, you can see this section called CFA, a bridge between fields. This is a nice way to see how CFAs connect different disciplines. In machine learning, data plays the role of parameters that we tune, maybe using gradient descent or gradient-free optimization. And in stochastic programming, CFAs are just a simplified way to express optimization under uncertainty. And in operations research, CFAs make those practical heuristics like buffer times or reorder points explicit and optimizable. And class 2 is done. What is next? VFA. Okay. Value function approximations. Let's switch. Alright. Well, this one is a big deal because it's the foundation of modern reinforcement learning, dynamic programming, and approximate decision making. So the main idea of VFA is that instead of directly choosing actions or solving optimization problems, we approximate the value of pain in each state. Once we have that approximation, we take decisions gradually with respect to it, making we pick the action that looks best according to our estimated value function. And here the mathematical expression looks like this. Okay, you can see, and I won't read. And this means you are choosing the action that gives the highest immediate contribution plus the discounted estimated value of the next state. And now this idea comes straight from Bellman's optimality equation, which is the backbone of dynamic programming. The exact Bellman equation says that V star of S equals the max over x of C of S, x plus gamma times the sum over all S prime of P of S prime given S, x times V star of S prime. The problem is, for large real-world systems, this exact computation is interactable. The state space explodes, the action space can be continuous, and the transitions are often unknown. So what do? We approximate the value function. Okay, we define a parametric function here, v hat of s given theta, that tries to mimic the true value function. This function can be linear, piecewise linear, polynomial, or even a neural network. And essentially we are saying we can't compute the exact future rewards, but we can learn an estimate of them. Now, one of the main challenges here is what we call the three curses of dimensionality. What are they? State space, the number of states grows exponentially as we add more variables. Action space, even if we know the states, optimizing our all possible actions can be very difficult. Outcome space, the compute expected values, we would need to know all possible next states and their probabilities, which is often impossible in practice. Okay, and let's continue. Now, value function approximations mainly address the first curse, the state explosion, by using function approximation, but we still need to handle the other two through clever algorithms. Now let's talk about basis function design, which is a important part of value function approximates. If we use a linear structure, the value function looks like this, you can see. And here, each file is a basis function, and how well the model performs depends a lot on how we choose them. And there are different ways to design basis functions. What are they? Separable, break the value into parts for each state variable. Piecewise linear, create breakpoints in the state space to capture nonlinearities. Polynomial, include squared, cubic, or higher order terms. And like S1, S2, S3. And RBF kernels use Gaussian basis functions to capture smooth nonlinear behavior. And training part is here. Here we use techniques like temporal difference TD learning, which is central to reinforcement learning. You will see parameters like the learning rate alpha, which controls how fast we update our parameters, and the discount factor gamma, which determines how much we care about the future rewards. Okay, the TD0 update rule looks like this. You can see theta is updated by adding alpha times the TD error multiplied by the gradient of v hat with respect to theta. And that bracket term is the TD error, okay, or temporal difference error, and it measures how wrong our current value prediction was. The algorithm keeps adjusting theta to make that error smaller over time. And when you run this learning process, you will typically see something like the chart on the screen. The Bellman error and TD error both start high and gradually decrease as the model learns. Let me show you Bellman and TD error, and here. And that's what convergence looks like. Now, under the hood, I want to show you some things. Let's stop here. Okay. There are several value function approximation algorithms that all use the same idea. Temporal difference methods like TD, lambda, and SARSA, and Q-learning, which is an off-policy method used in algorithms like DQN, policy iteration here, including approximate policy iteration here, and match methods like the least squares TD or LSPE. And each one has its own trade-offs between stability, convergence, and computational cost. Of course, there are also convergence challenges. For example, simple tabular TD converges under certain conditions, and linear value function approximations converge to a projection of the true value function, but with nonlinear function approximations like neural networks, convergence is not guaranteed. You can even get divergence. And there is something called data right. What is that? When you combine function approximation, bootstrapping, and off-policy learning, things can be unstable. So value function approximations are powerful but delicate. They require careful tuning and a good understanding of the system you are modeling. Now, when do VFAs really shine? They work great when the state is Markovian, the value structure is separable, and you can design good basis functions. The action space is high dimensional. The environment is relatively stationary, but there struggle when states have complex or non-Markovian dependencies. It's hard to engineer basis functions, and the system has rolling forecasts or time-dependent patterns, or when there is a strong combinatorial or network structure. That is Alan and DLA, direct look-ahead approximations. So, if you remember the previous methods like PFAs, CFAs, and VFAs, were about approximating policies, costs, or value functions. But here, with DLA, we do something different. We directly optimize over a sequence of future decisions. We use an approximate model to look ahead multiple steps, plan what we are going to do, then execute the first decision, observe what happens, and replan. It's like how a chess player thinks several moves ahead but recalculates after every move. And mathematically, the ideal formulation is something like this: maximize over all future actions the expected sum of discounted contributions. In notation, we would write like that. And of course, this is idealized and generally interpretable for real-world systems because we would need a full stochastic model of the world. So we build an approximation, we use a simplified or estimated model, okay, and written as like that, and we limit the planning horizon to h steps. And this gives us a tractable DLA that can actually be solved. And here, two being, what are they? Deterministic and stochastic. In deterministic look-ahead, we assume the future is known or forecasted, replacing and I mean replacing the random variables with predicted values. And that's how you get algorithms like shortest path planning, think Dijkstra or A star, and model predictive control, which is widely used in process control and robotics. It also includes rolling horizon procedures, where you solve a finite horizon problem, execute one step, and shift forward. And this deterministic version is the one most people use in practice because it's computationally efficient and relatively straightforward. Stochastic look-ahead version, on the other hand, tries to account for uncertainty explicitly. It does this using scenario trees or sampled paths. That's where techniques like stochastic programming, Monte Carlo tree search, robust optimization, and stochastic dual dynamic programming come in. They model uncertainty through multiple features and optimize across them, but that's also what makes them computationally heavier. And let's connect this with model predictive control, one of the best known examples of DLA. The MPC algorithm works like this. At time t, you solve an optimization problem over a short horizon, say from t to t plus h. You execute just the first action from that plan. Then, when the next time step comes, you observe the next, new state of the world, update your model, and solve again from t plus 1. This is called the receding horizon principle, and it gives you adaptivity without needing a full stochastic model. And here, clicked OK. If you look at how horizon length affects performance, there is a clear trade-off. As the planning horizon increases, the policy quality or average reward generally improves. But at the same time, computation cost grows rapidly, and deterministic DLAs gives you a good balance of speed and quality, while stochastic ones can perform slightly better but are much slower because of the need to simulate multiple feature scenarios. And let's switch here, characteristics and problems. Okay. Well, DLA frameworks also use several approximation and strategies to make this optimization feasible. For example, we might simplify the model dynamics, roll out using a simpler policy, approximate the terminal value at the end of horizon, reduce the number of scenarios we consider, or simply limit the horizon length. Sometimes we use heuristic solvers instead of exact ones or aggregate states to keep the problem small. And these 7 approximation strategies together make DLA practical for complex real-world problems. Okay, and when we look at the computation side here, deterministic DLAs with a short horizon, say h equal 5, are typically fast. Stochastic DLAs with 10 or more scenarios are moderate, and full scenario trees, where we explicitly branch all possible outcomes, can get very slow, but in exchange for this cost you gain robustness and adaptability. And what makes DLA so powerful is its balance. It leverages the structure of optimization problems, meaning it naturally respects constraints while being transparent enough that stakeholders can interpret the plan. It is also robust to model errors because the look-ahead then replanning steps let it self-correct over time. That's one reason MPC is so dominant in fields like energy systems and manufacturing. And there's that which combines the strengths of DLA and CFA. The idea is to start with a deterministic look-ahead, but then introduce parameters theta to handle uncertainties similar to how CFAs do it. And those parameters are tuned in simulation, giving you computational efficiency of a deterministic model, but with the adaptability of a stochastic one. And it's a clever hybrid that bridges model-based control and data-driven learning. And here planning, okay. In terms of applications, DLA shows up everywhere. In network problems like routing, vehicle dispatch, and logistics, it fits perfectly because these systems have a natural optimization structure and need fast, transparent decisions. And in process control, especially in chemical plants and energy systems, MPC dominates. It's the go-to approach since you already have good physical models. And in planning problems like production scheduling or resource allocation, TLA captures time-dependent structure explicitly, making it ideal for dynamic environments like supply chains. So, final part is here. Okay, so far we have looked at the 4 major policy classes, and each with its own philosophy for making sequential decisions. Now the question becomes, how do we actually choose among them? If you look at the chart, you will notice that each class exists in different dimensions: simplicity, speed, transparency, scalability, and optimality. Policy function approximations sit at the top in terms of simplicity and speed, easy to communicate and fast to implement. And they are the rules of thumb that often dominate real-world operations like base stock policies in inventory or threshold rules in trading. And let me show you cost function approximations here, blue region, are a bit more structured. They give up a little simplicity for better optimality and robustness. They are great when you already have a deterministic optimization model and you just need to tweak it to handle uncertainty. Value function here, look at this area, which push the boundary on optimality. Okay, like that, you can see it is 90. They can, in theory, approximate a true dynamic programming solution, but they pay for that power with higher complexity, more tuning and less transparency. DLA is here. Emphasize foresight. They optimize directly our future actions, which makes them more transparent than value function approximations, and sometimes just as powerful, but they are computational heavier. And deterministic DLAs strike a nice balance, not as simple as PFAs, but more explainable than deep value function methods. So there is no single best class. It depends on the problem. And let's look at decision framework. Okay, the first question you ask is, does the policy have an obvious structure? If yes, start with PFA. For example, in inventory management, where you reorder when the stock hits a certain threshold works beautifully. The same goes for trading strategies like buy low, sell high. If there is a clear optimization problem underneath, something with cost functions, constraints, or well-defined objectives, then you look at CFA or DLA. CFAs are great when you can parameterize a deterministic model, while DLAs are better when you need explicit multi-step foresight. And now, if your system's state is Markovian and you can design good basis functions, then VFA might be your tool. That's where you'll lean into approximation and learning, especially if your problem involves high-dimensional state space or continuous control. And for routing or network problems like vehicle dispatch or logistics, DLA is usually the best fit. It naturally aligns with optimization structures like shortest path formulations. And finally, if your environment is messy, I mean complex, interactive, or time varying, you probably want a hybrid method or a parameterized DLA that combines the strengths of multiple classes. Okay, and here, when you apply this reasoning across domains, patterns emerge. In inventory management, PFAs dominate because policies have clear interpretable rules. For energy storage, where we deal with rolling forecasts and constraint optimization, CFAs or DLAs shine. In vehicle routing, DLA wins again because of its explicit planning nature. Game playing systems often rely on hybrids, mixing tree search with value approximation, like AlphaGo did with Monte Carlo tree search and narrow value networks. Financial trading leans toward PFAs because human understandable rule-based strategies are still incredibly effective, and robot um, control blends VFAs and TLAs. You get continuous learning from the value function side and precise preceding horizon planning from the look-ahead side. And hybrid policies here. That's where the lines blur here. And actor-critic architecture is a perfect marriage of PFA and VFA. The actor chooses actions while the critic estimates values. And Monte Carlo tree search blends all four ideas. It uses DLA for tree-based look-ahead, VFA for evaluating leaves, CFA for upper confidence tuning, and PFA for rollout policies. And parameterized DLA is another elegant hybrid, combining DLA's optimization foresight with CFA's tunable parameters, and approximate dynamic programming with look-ahead merges VFAs for terminal value estimation with DLAs for tree-to-horizon planning, essentially embedding learning into the planning process itself. And if we zoom out for a moment, there is also an interesting divide between academia and industry. Academic research tends to gravitate toward VFAs and stochastic theories because they are mathematically rich, theoretically grounded, and publishable. Roughly three-quarters of reinforcement learning papers live in that world. Industry, however, values transparency, speed, and robustness, so companies tend to favor PFAs, CFAs, and deterministic TLAs, simpler models that are easier to explain, audit, and implement in production. And finally, that brings us to the core principle of the entire framework. There is no universal best. Each class can be optimal or nearly optimal for the right kind of problem. The real power lies not in picking one favorite but in matching the problem structure to the policy class strengths. If your problem is simple and well understood, go with PFAs. If it is a deterministic optimization with a touch of uncertainty, CFAs fit perfectly. If it is a complex, high-dimensional dynamic system, BFAs are your best friend. And if it's a multi-step decision-making problem where foresight matters, then DLA, especially the parameterized or hybrid form, will likely give you the edge.